Hi, welcome on yet another talk on device tree on this conference. My name is Tomasz Figa. I'm a Linux kernel developer at Samsung R&D Institute Poland. I've been working with Linux kernel for the last 6 years, and for the last 2 years I've been involved in board bring up and device tree support on Samsung Exynos SoCs and various related tasks. Basically, last year I joined the effort to improve the way we work on device tree and develop device tree validation tools to help our work. And in this presentation, I'm gonna tell you a bit about the history of our work and introduce the problem and propose solution for it. So I start with a quick introduction to the device tree itself for people that possibly haven't worked with it yet. Then show you what's happening with the data contained inside the device tree. Then I'll move to showing what's wrong with the processes that are currently used to process the device tree data and why that's wrong. Then I'll say a bit about the history of work on device tree validation and introduce a proposed solution that was posted some time ago to hopefully finally solve the issue. Then at the end of the presentation, there will be some time allocated for questions. So let's start with quick introduction to the device tree itself. As you probably know, there are certain architectures that have hardware devices that can't be detected in an automatic way. This makes a need for a way to provide information about such devices to the operating system. And so one of the examples of such architectures is ARM. Basically, there are two ways to work out this issue. One is just hard coding all the necessary data in the operating system itself. And this is what we did before in Linux kernel with board files. Another one, probably the best way, is just separate the data from the operating system and use a dedicated data structure to pass any necessary data to the operating system. And so device tree is one example of such data structure. As you can see on the slide, on the picture I prepared, device tree has a tree-like structure that represents more or less the topology of devices in the system. And so device tree is just a way to provide any necessary information to the operating system about hardware that can't be detected in an automatic way to let the system properly configure and access the device at runtime. And an example of data that can be passed using device tree are various resources needed for the device, or like MMIO addresses, interrupts, GPIO pens, or clocks. Another kind of information, a bit less common but also possible, is representing relations between devices, such as display controllers and display panels, or camera interfaces and camera sensors. And so such data structure, packed with a lot of interesting data, is passed at boot time to the operating system by bootloader and other kind of firmware, so that all the platform-specific data is separated from the operating system image. So let's start with some terminology to make sure that the words I use further in the presentation are well understood. Starting with a property, it is a key value pair where the key is a string that is name of the property, and the value is just an arbitrary set of data, such as strings, integers, or basically any set of bytes. A node is a set of 0 or more other nodes and 0 or more properties. And as well as properties, a node can have a name. Then there are bindings. Bindings are a description of how a device can be described using device tree. Basically, bindings define the way the operating system should read the device tree to get all the needed information about the device. There is a special kind of property. It's called compatible. It is a string that determines the binding to use for a particular device. Now, a few words about device tree adoption process. Device tree is not really a new concept. It has been used for quite a long time on architectures such as Spark or PowerPC. Later, it was adopted by ARM architecture as well. But also, a number of other architectures are using device tree to provide information about the hardware, as listed on the slide. As of Linux 3.14, there are more than 600 in-tree board device tree sources, which are files that describe particular boards supported by Linux kernel, and more than 4,000 compatible strings defined, which loosely translates to around 4,000 different IP blocks supported by Linux kernel, including various variants that are using the same driver but differs in some certain integrations or something. Adoption of device tree by the ARM architecture has greatly affected the amount of activity happening in the Linux kernel tree related to device tree. As you can see, since Linux 3.1, when initial device tree support was added for the ARM architecture, the numbers of both Dtss files and binding documentation files have started greatly increasing. This means much more patches being sent to respective mailing lists, much more changes happening in kernel tree, and possibly much more errors to catch at review stages. After this quick introduction, it's time to dive a bit more into device tree internals. Let's see what can a device tree look like and how the data inside is being processed right now. So here we have the first widely available form of device tree, which is the Dtss, or device tree source. It is the plain text human readable form of device tree that is widely used by developers to describe the hardware they are working with. Here a node is represented by a name string and contents between a set of braces. Let's see if it works. Okay, so here we have a node. And a property is just a property name, equality sign, and optionally a value. Okay, so here we have a property. Thanks to its human readable representation, it's the most developer and also Git-friendly representation, but it's hard to parse by computers. And so we have device tree blob, also known as DTB. It is a binary file stored according to a binary representation called flattened device tree. It is designed to be processed efficiently even by slow processors, So there is no text parsing involved to read data such as property names or property values. An useful property of FDT is that kernel code can simply store pointers to data of DTB stored in memory to address property names or stored values. So there's no text parsing involved. There are more than just those two representations, but they are quite uncommon, so let's not cover them here just for simplicity. And so we have device tree compiler, which is a tool that lets us convert the device tree between various representations. The two I presented before and a few more ones. Basically, it's a simple tool that translates input data into desired output format. Nothing to really talk much about. So now you might be thinking that this is all very simple and be wondering whether any issues could be even introduced by this kind of process. But now let's take a bit closer look at how Dtc performs the translation. Basically, Dtc just parses the input data into internal representation. And then performs nearly direct translation of all the nodes and properties into output representation. So basically, every node and property reaches the output file almost directly as in input file. There are some simple checks done on selected properties and nodes, but there is no complex validation mechanism that would verify if device tree complies with defined bindings. So let's see an example that illustrates the problem. Here I have prepared a sample device tree source snippet with tree representation of a few device nodes. There are a few errors injected in these snippets. Could you tell me how many errors you can spot there? Anyone?
The interrupt.
Let's wait for the next slide to show the answer. Okay. Anyone else? Okay. So there are 3 errors there. Basically two simple typos, which can happen quite often. Control error with triple L, calls instead of cells, and a simple data error, which is an error in specification of an interrupt signal. As you can see, the weak interrupt controller uses one interrupt cell, and there are 2 interrupt cells provided in the SDHCI node. But wait, let's see how Dtc handles that. After executing the necessary command using the Dtc distribution inside Linux kernel tree, we see that it completes successfully, producing a DTB file with exactly the same contents as in input file. But well, does it mean that the Dtss was valid? I don't think so. I can't get used to that. So this brings us to the topic of device tree validation. If we could take the existing binding specification and use that to automatically validate the device tree data, we probably would have much less work at review stage or at all when debugging issues. Unfortunately, current situation isn't that good. We have a number of bindings specified as plain text documentation files inside Linux kernel source tree. They are documented using a human-readable format, which is not specified. So it's up to the imagination of the bindings description author. So this basically makes such text files almost impossible to parse unless you are willing to provide a parser for every existent format of bindings. But even then, you wouldn't get all the needed information from those files. And so currently, the only way to validate device tree data is by using intelligent beings such as maintainers. But, well, this is not really what we want because they have better things to do. So there is a first conclusion of this presentation. Basically, we need a formal way to describe DT bindings, something that we could use inside some software that would automatically validate the Dtss or other DT representation, whether it complies with defined bindings. And so, a need for this was already noticed in March 2012 by John Smurl, who started a thread on device tree discuss mailing list. In the XML world, you can make schemas that describe what is legally allowed in an XML document. Device trees don't seem to have any kind of schema mechanism describing what is and isn't legal to put in a tree, he wrote. Instead of recreating the entire world of schemas, has anyone looked at using XML schemas to define what is a valid device tree and then write a tool to validate the existing device trees, he asked. Unfortunately, the topic didn't receive much attention at that time. And only after a discussion happening much later, in July 2013, on Linear Connect Europe conference, some effects have started to show up. And so in September 2013, an RFC by Benoît Cousin and Fabien Parent was posted, and it brought us a Dtss-like schema language which could be used to describe existing bindings. It was very simple, readable, and in general nice, easy to work with if accustomed with Dtss syntax, but well, the solution turned out to be not flexible enough because there are certain bindings that couldn't be described using it. And so then I came with my RFC, posted a month later. It was just another Dtss-like schema language, which was supposed to be much more flexible and cover much more constructs used in device tree bindings, and even things like relations between particular properties. But unfortunately, this made the language very complex, hard to work with, and in general, not nice. And it was still not flexible enough. Let's see why. So here we have an example, basically a real-world example of a bus that can support per-slot interrupt signals and 60-bit wide address space. So here we have the bus node and some interrupt-related properties. And here we have a sample device. Note that there is certain issue with this because interrupts of particular slots are connected to an external interrupt controller described by a node labeled int_c. So here we have an interrupt map property which maps interrupts of particular slots into interrupt signals of the external interrupt controller. And here we have an interrupt specifier for the device that is basically an index into the interrupt map property together with address cells entries of the rec property. It is quite complex because to parse the interrupt property in each interrupts property in the device node, you need to parse first address cells, interrupt map mask, and interrupt map properties of the bus node. And then again, to parse the interrupt map property, you need to parse similar properties of the int_c node. So you have quite complex relation between several properties, which is not easy to represent in a simple schema language. So here we have a second conclusion, that a schema language is unlikely to cover the most complex bindings. So we need something else, and such something else have been posted by Stephen Warren. He used a completely different approach, which instead of inventing a Dtss or another schema language, just decided to implement validation of every property, every DT bindings just directly in C code of the device recompiler. The biggest advantage was probably the ease of learning this, because all the kernel developers are supposed to know the C language very well. So another advantage was that we all know how powerful the C language is, so you just could write anything needed to validate any binding. However, this turned out to be also quite a drawback of the solution, because every even trivial binding ended needing a piece of code in Dtc to validate. Still, it was the only solution that could validate interrupt bindings completely. And so we go to yet another proposal of solution, which is a hybrid approach based on all the previous attempts. Posted by me in February this year. It is a hybrid solution that can use C code to describe complex generic bindings with complex relation between properties such as interrupts or other bindings like this. And a simple schema language that can cover most of the simple device-specific bindings to eliminate the need of having C code for every from the 4,000 defined bindings. And so, let's first separate two classes of device tree bindings before diving into implementation details. So, when looking at currently defined bindings, we can define two classes. One is generic bindings, which are used across multiple device-specific bindings. They need to be quite flexible to cover all the devices using the same kind of resources or represent relations completely. So they end up often being quite complex, especially to describe using a schema language. And so for them, we can use C code directly just in the proposal of Stephen Warren. But then we also have specific bindings that are device-specific and are mostly consisting of generic bindings, such as GPIO pins, clocks, interrupts, and so on. They are repeatedly used by multiple devices. Sometimes a device-specific property, also, device-specific binding also requires a number of simple device-specific properties, but they are mostly simple, such as integers, strings, or arrays of them. And another characteristic of those bindings are that there are lots of them. Basically, every device supported by Linux kernel and other operating system using device tree needs a binding defined, even a trivial one. So having them described directly in C would need a lot of patches being applied to DTC to support every new device. And so the proposal introduces DTS-like, yet another DTS-like schema language, but this time much more simple. So here we have one node per binding to describe the list of generic bindings used by particular device-specific bindings, the list of simple properties needed, and also to match a binding to certain nodes in device tree, there is a match keyword to specify the matching key for the binding. And so to cover multiple possible matching options for bindings, we have currently 3 possible matching types. The first one, probably the most common one, is by compatible string. The second one is by absolute path of a node in the tree, and the third one is by the value of device type property. The last 2 are used mostly to support verification of special bindings such as CPUs or memory nodes that don't have compatible string or have compatible strings but can't be used to bind them to particular bindings. At the moment, only one matching type is supported, but if needed, this might be changed. It will be a simple change in the code. Based on analysis of existing bindings, it turned out not to be needed right now. So the DTS language also allows listing of simple properties, as mentioned before. At the moment, the schema language just specifies specifies the list of properties without any type checking yet. Because as you probably seen on the interrupt bindings example, it is quite hard to specify the contents of some properties. But on the to-do list is adding support for simple types such as integers, strings, or arrays that don't depend on other property values. Also, you can check constant values of properties. This is useful for properties like address cells, interrupt cells that are required by bindings to always have certain value. And you can also mark properties as optional by the optional keyword that makes the validator just ignore if such property is missing. Now the most important feature is referencing generic bindings from the Dtss schema file. There are 2 keywords, require and use, that can trigger calling the C code responsible to validate a generic binding directly from the Dtss file. So you add the require or use keyword, specify name of the generic binding, and then optionally list some arguments that should be passed to the C code to customize the binding for device needs. The difference between use and require keywords is basically the same as with property with or without the optional keyword. The use keyword makes the tool treat the resource or the generic binding as something optional. So it fails only when there are parsing errors, not when properties are not present. Also, the arguments represented here as properties inside the Dtss nodes are available inside the C code just by parsing them like parsing a device tree. So basically, this looks like a device tree for device trees. So here is the way of operation of the DTC extended to support validation using DTSS schemas. First, it scans available DTS files and builds an index of matching keys to let it match all the nodes to respective bindings. Then for each node in the input tree, all the matching DTS schemas are executed, which means that for each matching DTS schema, presence of required simple properties is checked, and necessary C code is executed to validate the generic bindings referenced from this DTSS file. Then the tool issues any error messages or warning messages if any of the conditions are not met. So let's see how it works in practice. I have prepared a sample schema file which covers the example shown before with ARM-PL 192 VIC interrupt controller and Samsung S3C6410 SDHCI controller. As you can see on the slide, the VIC controller requires the VIC controller is an MMIO device that requires one reg entry in device tree and is an interrupt controller that requires 2 cells per interrupt specifier, 1 cell per interrupt specifier to match the interrupt to match with the interrupt signal of the chip. And the SDHCI is very similar. It is an MMIO device with 1 reg entry, and it is a consumer of 1 interrupt signal. Now, after entering the necessary command line and passing this sample schema file to the modified DTC, we can see that we get a number of warnings about no schemas present for selected nodes, as there were just 2 schemas on the example, and 3 errors telling us that there is no interrupt controller property in first VIC node, and there is no interrupt cells property in second interrupt controller node, and that the parsing code couldn't parse first entry of interrupt property in SDHCI node. So as expected on the first example, there are 3 errors. As you can see, it works. Now, this is what we have right now. Now we should try to think a bit about the future. We have quite a number of to-do elements on the list. First of all, few review comments were posted on the mailing list, mostly about implementation details. They need to be addressed, of course. But also, we have on the list some extension of the DTSS language to let us specify subnodes of selected DT bindings. Also, simple type checking for simple properties such as cells, strings, or p-handles, or arrays of them. Also, the verification could be made a bit more strict. Currently, properties that are not matched by any schema are not reported, but they are supposed to be incorrect. They should be reported as well. at least as a warning. One more idea for future is generating binding documentation directly from the Dtss files that would completely replace the currently existing text files in the kernel. So we could just have the machine-readable specification and then automatically generated documentation without duplication the same information. And of course, last but not least, probably most of the work required for this point is implementation of all the bindings available currently in the Linux kernel or in other sources. As I mentioned before, there are lots of them, and they need to be implemented either by providing necessary Dtss files or directly in C code. So quite a lot of work to do. And this is where we are counting on your contribution, because this is a very important topic for anyone working on the device tree, working with device tree, and I believe it deserves much more attention that it is receiving currently. So please consider helping us to achieve the goal and eliminate one of the biggest issues of device tree. Well, thanks in advance. Now I would like to take the opportunity to thank everyone I mentioned on the list on the slide, and probably everyone I forgot to mention. Especially Samsung Electronics Poland and Linux Foundation for letting me be here today, and also all the device tree and kernel community for possibility of working together and all the fun we had. Thank you. Okay. Oh yeah, thank you. So here we have some time left for any question if you want to ask me. Also, there is some contact data listed on the slide. The most preferred are first. Okay. So questions? Yeah.
Could this be also used to provide some sort of automated editor to device trees, so that you could actually have, say, I'm starting to write this device tree, if I put this, and this in, can you give me template information that would say, these are the nodes I need to fill in to make this device tree work?
Okay, so the question was whether this could be also used to make an automatic tool for editing the device trees. And I think, yes, at least the binding specification could be reused to build a tool for editing the device tree, as having all the properties or nodes needed to be provided in the device tree gives you a way to specify what needs to be added to create a tool that just takes that just presents you a list of defined currently compatible strings. So you could select the one you want, and present you a list of the needed properties, and probably limiting the ranges of data that could be entered as a value. So probably this is yet another step to do. We should add that to the to-do list. But first, I think we should focus on making sure that we can cover all the bindings. So as I listed on the to-do list, we have to add support for subnode specification, or so some type validation. Okay. Is it all you needed to know?
That's what I was thinking about.
Okay.
It certainly would make people's life easier for them. I mean, to say, write new boards and boards, to be able to have a tool which would take the base SOC stuff and then say, this is what I'm adding to my board, and then output a Dtss file with the kernel build.
Yeah, I can really imagine this sort of tool being very useful, as I'm working on bringing boards every day, so that would be very useful to have. Feel free to post the idea on one of the mailing lists. Yeah?
2 questions. Do you have a Git tree with this?
Excuse me?
Do you have a Git tree published with?
This is just distributed in a form of patches right now, so you can find on the few patches posted on the DT compiler mailing list by me in the February. Maybe I should set up a Git tree.
The second question is, for some of the generic checks, like interrupt checking, have you run it on all the device tree files in the kernel?
No, I would have to, the problem is that you need to have a list of device-specific bindings that instantiate the generic checks, because you can't rely just on property names or certain subnodes, or you just need to know that this kind of device wants this property to be the generic property, not some internal property of the same name. So basically, you need to trigger checking of those generic checks by those by those device-specific bindings. So I would have to define the Dtss files for every existing device-specific binding, well, that would take me quite some time. So I just tested some of our internal Exynos DTS files, found quite a bit of, quite a few of simple errors, but nothing really special, as we've been doing quite well yet with the review. But as the numbers are getting bigger and bigger, we will have less and less time to review the patches, and so something automatic is really needed. Okay, so was that the answer you wanted?
We can talk more.
Okay. Yeah, you can always send me an email or find me on Freenode, IRC, on the device tree, ARM Linux, or probably a bunch of other channels. Or probably the best option would be to just send an email to the device tree or device tree compiler mailing list for all the people to be able to read them. Yeah?
Is there a concern that if there's all these bindings, and if we have a huge set of complex ones that require a lot of C, is the device tree compiler going to get huge and unwieldy, or is managing that pretty good?
Looking at the bindings, the question was whether there is a concern whether the Dtc, the device tree compiler, wouldn't get too big by adding C code for all the complex bindings. So, well, of course there is some concern, but looking at the bindings already existing, we don't have that many generic and complex DT bindings. They aren't showing up so often, and they aren't being changed that often. So with the limited number of such bindings, I think we can somehow handle this. Yeah.
Third on that point, we've got a bit of the C checking. Would it be better to have some sort of scripting language implementing that checking, so we don't have to have it all in DTC?
Yes. The question was whether it wouldn't be better to have some scripting language instead of the validation code written in C. And we've been thinking about this kind of idea. And probably it would be quite useful to have a scripting language, but well, there is no strong opinion on this yet. We need to probably we need to have some more discussion on this. At least right now we don't have that many bindings implemented in C already. So. But still, one more point of having the bindings defined in C would be sharing a lot of code between the kernel and the Dtc, because you can validate the bindings just by parsing them as the kernel does. So currently, for example, I have implemented the interrupt parsing just by copying and pasting and pasting the interrupt parser code from the kernel. So yeah, I probably forgot to mention on the to-do list that it might be good idea to separate the parsing of generic code, the generic binding parsing code from the kernel into some kind of general library and reuse that in the Dtc.
It's called libfdt.
Oh, not exactly, but well, probably this should be more like libdt. Yeah, FDT is just for parsing the specifics of FDT.
Well, there's two types of parsing. There's the flat byte-tree parsing, and then there's the unflattened parsing. The unflattened part has a lot of kernel specifics in it.
As I observed during my work, the kernel parsing code can be adapted quite easily to fit into Dtc, so probably making a library out of it could also work, but this needs definitely more discussion.
But there's also expanded use of libfdt coming and like address translation support. So that
doing
it in the flat device tree.
Honestly, I would need to look more on the libfdt, but my experience from working with libfdt got me to a conclusion that it is a bit too limited right now. It needs to support a bit more parsing than it does currently. Okay, any more questions? Yes, please. Okay.
A little bit out of scope for what you're talking about, but a lot of stupid errors in DTS files lead to rather cryptic compiler errors. Do you know, is anybody working on enhancing those errors in any way, or?
Yeah, I implemented. So the question was that the Dtc compiler, whenever approaching some simple syntax errors, gives us quite cryptic messages without any reasonable explanations of the errors, and whether I know anyone working on this already. So the short answer is that unfortunately I don't know anyone working on this, but I found this issue to be quite a bit related of the Flex and Bison used to build the Dtc compiler, as it doesn't give too much diagnostics, at least in current implementation. So this is probably yet another topic that could be started on one of the mailing lists and maybe picked up by one or more of the Dtc maintainers. Okay, you have your question.
On the previous slide, you suggested to try your tool. So
yes.
There was an answer already that you don't have a Git anywhere, so it's only to just writing to you and you provide a link?
As I said, there are patches floating on the device tree compiler mailing list, so you can clone the Dtc repository and apply 5 or 6 patches from the mailing list. There are archives available of the mailing list. But yes, I think it's a good idea to set up a Git tree and post a link to it. I already have an account on kernel.org, so I will set up one there. Okay. Anyone else? Yeah?
Did anybody other than that first post that you put up there ever consider using XML instead of your Dtss-like schema?
So the question was whether anyone except the first poster ever considered using XML for this. So on the discussion on Linaro Connect in 2013, we got to a conclusion that syntax similar to something kernel developers are already used would be more convenient to use. probably XML could be used for this, as the schema language is quite complex, but personally, well, maybe that was just a matter of several personal decisions, but well, I think there is no good opinion on XML around kernel developers. Okay, I guess that sums up the presentation. So thank you very much for your time. Hope you liked it.